Welcome everyone to Science Society, and of course, a special welcome to you, Lotte. It's such a pleasure and honor having you here. Your research is so interesting. So, before we get started, let me give the audience a short introduction and ask you a few questions so we get to know you a little bit before we go dive deep into your research. So, you're at the University of Amsterdam and the Leibniz Institute Dresden, and you are doing studying the or you're balancing theoretical physics with with different with experimental physics, as far as I understand, right? Is that correct?
Well,
Or
I work with experimentalists, but I'm not very good in a lab, so I keep to the theory.
okay,
Uh,
good.
yeah.
So you collaborate with
Yes.
experimental, and you also teach and you're now doing also research on different projects, which is also really which are also really interesting, and you want to understand everything from general relativity to condensed matter perspective by studying analog black holes and foundations of quantum mechanics and child density waves. And your work recently has had a lot of attention and got picked up by international media and different media outlets around the world. Um, and yeah, your recent article was also discussed a lot by different popular science outlets and resources. This is wonderful. I mean, you were still quite early in your career, and your research has had a lot of attention. That must be really a great feeling, like rewarding that people care about your research. So, how did you become a scientist? Was it like a childhood dream, something you always wanted to do, or did something spark your interest? I don't know, maybe a trip to the museum or a class, or maybe a family member, a teacher, whatever it is. We would love to hear the story. Thank you.
Yeah. Well, thanks first for inviting me here. I'm really happy to talk about my research, and indeed, it was amazing and a bit unexpected that this research got picked up so much. And really nice because I also get like a lot of opportunities to now present about it, like here. Yeah, and your question, how did I become a scientist? I actually didn't know what I wanted to be when I was a child. I didn't really think about becoming a physicist. Most people where I grew up were not scientists. There was no university in my hometown. So I for a long time I thought I'm gonna be an artist because my mother was. Yeah, or archaeologist, maybe a tree doctor because I wanted to help nature. So I had really no clue. But then I went on a gap year, and I actually found a book of Stephen Hawking, A Brief History of Time, inside a second-hand shop in Portugal. It was the only English book, well, out of 10 or something. And I read part of it, didn't understand most of it. I hope I could now. But that was the moment for me that I was like, oh, this is something I want to know. This is what I want to understand. I want to know how the world works. And I think physics for me turned out the way to do that. Because of course the world is big and you can do it in many different ways, but you have to find the language for which it works for you. And it turned out for me that was physics. So I started studying it and never regretted it.
That is such a beautiful story. First of all, Portugal, I'm originally from Portugal, and then that this book really sparked your interest or had such an impact on you that yeah, that we now hear speaking, and you did all this wonderful work. Um, that's really inspiring for also schools and everywhere having great libraries. So it's a really great story. And how did you then chose, this, in this case, this project? How did it come about? If you could tell us a little bit of a story there, I don't know how specialized it is, sorry, to study synthetic black holes or to simulate them. It sounds, for us that are not in the field, it sounds like very cool and fascinating. So how did you get to work on this, and yeah, and how did this collaboration get come together?
Yeah, so I did my master thesis also at the University of Amsterdam at my current supervisor, Jasper van Wezel. It was on a whole different topic about the foundation of quantum mechanics, but it was really nice. And then, well, halfway through the year, one of his colleagues from Germany came to visit, and they talked about this new research that was being performed by another group on this analog black holes, synthetic black holes, and how interesting that was. And they kind of came up together with a project, that we could maybe do together with a group from both Germany and the Netherlands. And then they wanted to hire PhD students on that, who could do like most of the groundwork, and that became me. They asked, well, they interviewed me for the position, and then we figured out it was a great match. Also because I've done some work on general relativity itself, but also studied quantum systems. So it really fitted into both these worlds that I both really liked. I think always had a hard time choosing. Maybe that was why it took me long to figure out what I wanted to do. I still have the same in physics, so I want to do all fields and understand everything. And this is a great way because you can like take a taste of both.
Yeah, I understand that you're feeling. I am still that way, and I'm not young anymore. That I have a hard time staying just focused on one thing. I have many interests, um, and I don't think. Do you think it's a bad or good thing? Because do you think for the future, with all the AI and computer power help we'll have, do you think we will need more people that have more various interests and know about different subfields, or do you think, we need both? I guess we need both, right? So we need
Yes.
people
Yeah.
that, yeah.
That's always the answer, right? We always need both sides of the coin. But it's important that you keep talking and that you combine those people such that some person maybe understands the very detailed plus or minus sign in this very exotic equation, and something else then can say, but this looks like this other field, and can we not combine it? And I think only when you work together with different people that have different specialities, that's when science progresses the most, even with AI.
Exactly. I agree. So, yeah, thank you for giving us kind of a background story. It was really interesting. It was a wonderful conversation. So, if you want to go now into your research, everyone has the link to your presentation, and the stage is yours. Thank you.
Okay, perfect. Yeah, I hope everybody found the slides then, because I'm gonna need them. The title of this talk will then be the radiating synthetic black hole, because it sounds really cool. And if you go to the second slide, those are all the collaborators. So it started with just the institute in Dresden and University of Amsterdam, but people moved and new people came in, and now we have this big collaboration between all kinds of people. That is really going great. We just got a grant for it as well to continue the work. And I want to thank all of them for their contribution to this. Okay, so today I will talk about black holes and synthetic black holes, and to do that, I think I will need to try to explain to you some of the most important physics in black holes and general relativity. So I will start off with that, and then also show you the first synthetic black hole ever thought of, and then continue on such that the talk becomes a bit more technical when we go into the condensed matter system, so the quantum side, all the way till we have thermal Hawking radiation inside this analog. And I will also add a piece where I will tell you about the experiments that we're now working on and some future work. Okay, so slide 4. Black holes, and what are they, and how do they form? So the first black hole that was ever mentioned was already in 1784, which is a long time before general relativity was actually formulated by the Einsteins. And John Mitchell described it as an object that was so heavy that nothing could escape. He didn't coin the term black hole yet, but that came later. But he was so far ahead of his field that nobody really paid attention to it. And only after the formulation of general relativity did it actually pick up. So how does a black hole form? Well, the most common way for how we think about this is that we first have a star, and a star is some kind of engine. So it burns the fuel inside, and by doing that, it creates a lot of energy, and this energy pushes outwards, and it pushes the matter that is inside outwards such that it balances the gravitational force, because, well, matter attracts and it wants to fall in, but this is cancelled by the explosions happening inside. And therefore you have a stable star. The sun, we see it, we're happy it's stable. However, there comes a point in the star's life, and if you go to slide 5, that the fuel runs out, and that the tank is empty. And then what happens is that this force that pushes everything out disappears, and you only have gravity left. And this gravity will attract all the mass inwards till things collapse and become smaller and denser, and a very tiny, massive ball is left. And if that mass is large enough on slide 6, you get a black hole. So why is it black? Gravity there is so strong that nothing can escape. So as soon as something is close enough to this very massive point structure, then it can never go out away. It can only fall further in. And therefore we call it black, because nothing comes ever out of it. So we will never see anything else than something being black. Okay, so that is the usual story of the formation of black holes. And I think it's nice to get an image of what they are. So far, if we go now to the present day, in 2019, they did the incredible feat of actually making a picture of a black hole. I hope you've all seen that. Maybe you also had a talk about it then. And there was this really nice photo. That was the first direct observation of a black hole ever. But we also have a lot of indirect observations, such as the gravitational waves that were detected when two black holes merge, and measurements like how does it influence the systems and the stars around it, which is amazing. But it's also kind of the only thing we can do: observe things that are already there and that are already happening. So let the universe make experiments for us. What I would like to do is take the desk that I'm sitting now and throw it in and see what happens, because then I can manipulate it or turn off gravity or change how they form, which would be very nice, but also very impossible, because, well, we can never reach them, and we can also not make them, which is good because it would swallow Earth. So we can observe them indirectly, but we cannot manipulate them, and we cannot experiment on them in the way we usually like as scientists. And therefore, parallel to the field of general relativity, there was also the field of analog black holes that came into being. So if you are on slide 8, so an analog black hole or an analog system is a system that has that is not a black hole, but it has properties, some, that are the same as we see in a black hole. This field is very old already. Like I said, it started when also the field of general relativity came into being, and therefore they have a lot of analogs in there, and I listed them all on the left in all kinds of different systems. So fermionate, Bose-Einstein. They even have atomic lattices where they place atoms in positions, and then they let the whole thing move to see what happens then. So there are really a lot of nice things going on in the field. And well, the reason is because such a system, which is not real but still similar, might be able to make an experiment, and then we can change stuff, we can tune it, we can, well, not really, but we can throw in a desk and see what happens. And that is kind of the goal of this whole field, to find these systems that are similar, and then to make them in the lab so that we can test our theories. Okay, so to explain the analog and the first analog, I need to explain a little bit more about black holes and black hole horizon. And to do that, on slide 9, I draw a very schematic picture of a black hole on the right. It's just a black dot. And then in the middle, I have a horizon. And I have these two observers. I have here a blue observer that's just chilling on a cloud somewhere. And then there's far away, there's this red observer that's standing on a rocket, but it doesn't matter so much for now. And the two like to communicate. They're friends, they want to send a message. So what the blue observer does is it sends a light pulse away towards the observer on the rocket. And because it's on the left of the horizon, nothing really strange happens. The light pulse here, it goes all the way to the left and it reaches the person on the rocket, and it can send a message back, and they can still be friends and talk to each other. But the force of gravity increases if you come closer and closer to the black hole. So if you go to slide 10, we have a third observer. And this observer is on the right side of the horizon. And it also wants to communicate with the two others. However, when it tries to send out a light pulse, the force on the light due to this black hole is so large that it exceeds the velocity of the light, and the light pulse is pulled inward to the black hole. It can never cross the horizon anymore. It can never go away. And this person on the rocket is not able to communicate with its friends anymore. It's a bit sad, but therefore don't fall into a black hole. It's not a good idea. So now we're back to this statement about black holes being black. Nothing can escape it, not even light, which is the fastest thing in our universe. So the rocket and the person can't either, and everything in the end will fall into the black hole. Okay, so on page 11, I have the first black hole analog for you. Here, Bill Unruh came up with a system where we have a similar behavior as I just told you, but now instead of light and light pulses being sent out, I have sound pulses. I will also have a horizon, and the observers of before are now the fish. For example, if you have one of the fish on the left of the black line, which will be the horizon, the fish says blop. And the blob travels in the water, it vibrates a bit, and it propagates, and then it reaches one of the other fish far away on the left, and they can communicate and send information, as far as fish do. However, again, on slide 12, we also have the fish on the right side of the horizon. And now if this fish says blob, and it's on the right side of this black line, then the velocity of the water, because it's closer to the waterfall, is going to be greater than on the left, and it might be greater than the speed of sound in the water. And when this happens, then the water will drag away the sound towards the waterfall end, and it will fall over and never reach anything left of the horizon again. So here I hope you see the analog of the situation we saw before. We have a region where we cannot communicate anymore, and therefore we have a horizon, and even though it's now sound, we kind of have a sound black hole. Yeah, that was the first thought experiment people come up. They didn't do this with fish, but they did do this with moving water. So that was already really nice. However, the only thing you can actually see is this horizon physics, and there's no very special things going on top of that. Also because it's just sound and water, so there are no quantum effects here. Okay, so on slide 13, I have some more general relativity for you. I think most of you will have seen the picture of the bending of space-time when you have this trampoline where you put in a massive ball and you put it on the trampoline, and then you see that, oh, hey, the trampoline, it will curve and it will form some kind of round around the object. And we know that that is how space-time works as well. So the force of gravity comes from the bending of space-time. Because if you have a hole inside your fabric, as the picture above, then if a particle comes close to that, then, well, it will go down and it will circle around instead of going straight through it. And therefore, this it kind of has an attractive force that you can write as our gravity. Okay, so on the top there's just these three balls, and on the bottom I've drawn for you two special spacetime. The left one is flat space, so there are no massive objects in here at all, nothing that curves spacetime, and therefore everything will just go straight and approximately how we see it in our everyday lives outside of the Earth. And on the right here, I have drawn a very schematic picture of what would be the gravitational potential, this curvature of space for a black hole. So the black fin again is a black hole, and you see that, well, it curves inwards and goes all the way down. So something that will fall will fall towards the black hole, and if this becomes very steep, you cannot escape anymore. Okay, so for flat space-time, we can see, okay, how does light now behave? Again, with the light pulses and the different observers that we already saw before. So on the left, I have the gravitational potential, and on the right, I now have a space-time diagram. So what I do is I plot space as on the x-axis and time on the y-axis, and then you can draw how light moves in the space-time and gravitational potential that you see on the left. And, well, because there is nothing weird in there that curves space-time, if you send out a light signal, there's nothing that influences it and will just go straight. And that's also what you see in the right picture, where you have this straight lines. You have the left, which is going towards the left, and then the right, you have going towards the right, and it can only have one slope because that's the speed of light. And it's nice because now these two observers, they can communicate, they can send messages, and they're happy. Now on page 15, I have again a black hole. And like I told you, nothing can escape from behind the horizon. Okay, can we then also see this from this space-time diagram? Well, the answer is yes. Now, what I've drawn to you is again these light pulses, but they are not straight lines anymore, but they are being influenced by the gravitational potential. So if you have the blue observer below, it can send out a light pulse towards the observer on the right, and everything is fine. But again, if we cross the horizon, which is all the way on the left, you see that this blue curve that represents how light can travel, it will become more and more and more vertical till at the horizon it becomes exactly vertical, and after it will even tilt over. And therefore, because it's vertical like the arrow with the light pulse, it can never go to the right again. So it cannot move away, and it cannot cross it. And therefore, anything trapped on the left is not able to communicate with the outside anymore. And we can't send anything back. Okay, note also that if I have the blue observer on the right, it also has the right light cone, and it's the light if it sends it inwards towards the black hole, which means that well, you can follow it and you can see that it reaches the horizon, the black straight line, and then will fall inwards towards the singularity. Yeah, okay, but general relativity is a bit weird, and not all observers see the same thing. Well, what do I mean with that? Basically, because this gravitational potential and something we call the equivalence principle, every observer has their own set of clock and a measurement machine that just as a stock something that can measure distance for you. and they change how they work for different observers. So if you are at a different place in your gravitational potential, or you're standing still, or you're accelerating, then you have a different clock, and you need your own clock to measure time, and you need your own measurement machine to measure space, like the distances. And that's a bit weird, but we can deal with that in the framework of general relativity and a lot of the mathematics that's going on there. And I will just show you now the picture of how things change if I consider a different observer. So on slide 15, I had an observer on the right that was laying on a cloud. It was doing nothing. And on the slide 16, I now have an observer that is standing on a rocket. So therefore it has an acceleration, a constant acceleration. Because actually this observer is very scared for the black hole, and therefore it tries to move away from it. And actually its acceleration of the rocket is meant to cancel the gravitational force inwards such that it doesn't fall into the black hole. And with the matrix of GR and Coulomb transformation, we can then also calculate what this person would see. So below I have an observer and it sends out light pulses. But then on the upper right, that is the observer that we think about what will it see. Okay, so if you have the blue again, so they try to communicate, it will just go from one to the other if it's on the right, and you can see that again the line becomes more and more vertical till at the horizon it's completely vertical and they cannot communicate anymore. But now something strange happens with the red. So before we had this red that went just inside the horizon, it went against it and then it can go through. And now you see that it curves upward. So instead of something falling through the horizon, it will approach the horizon, and only at infinite time, all the way up inside the space-time diagram, will it ever reach it. So if this observer on the rocket looks at the black hole, it never sees anything reaching it. It also never sees anything come out of it. But everything gets stuck on top of it. And that's interesting, and it's also how we recognize this horizon behavior. Yeah, so keep a little bit this picture in mind. I will show it a few more times. But I also lied to you a bit because black holes are not black. Well, Hawking figured out that you can have a process in which you have radiation coming outwards from your black hole. And this is so small that we don't see it. So in many, many cases, we can still just consider the black hole black. But there is this tiny bit of radiation that might sometime in the future, not in any foreseeable time, sadly, be measured. And then we can say that we have measured that a black hole is not actually black. So what is this process? Well, it's normally explained by the picture on page 17, which is shown that, okay, if you have a quantum vacuum, it can happen with some small probability that at some point you create a particle and an anti-particle at the same time. And normally, well, if you have an anti-particle and a particle, they meet again and annihilate, and nothing really happened. However, when you're close to horizon, it can happen that you have such a pair and that one falls into the horizon, and then the other one will be able to move away all the way to infinity. And that is such a Hawking particle that you can then observe as radiation at infinity, and that we can assign a temperature to it, which is called the Hawking temperature. Okay, so black holes are not completely black, and that is exactly the thing that we want to see in an analogous system. So we want to make an analogy for Hawking radiation, but then looking at nothing, not a real black hole, but a system that is similar to it. So that was our goal. So in page 19, I will show you what you need for that. Okay, so I already told you that if you have observers, they see different things. They have their own measurement machine for distance. They have their own clock, and therefore you can also approximate the gravitational potential they see locally, so close to them. So what do they measure with their clock and their ruler? Okay, so the global structure here on the left is just that we have a black hole again because we want this radiation. But then we can also try to see what will these two observers see. So the first one is the lazy observer that does nothing and will fall into the black hole. And well, around it, it will measure that things go approximately straight because of it falling in and not doing anything. But the scared observer that does not want to fall into the black hole, the wet one, it will see something very different because it's accelerating and it's static compared to the black hole, so it doesn't change its position. Now, if we start out with a system for the blue observer that is completely empty, so nothing is going on, no particles are there, it's just in a zero energy ground state system, there's still a black hole though, then we can translate what the red observer will see. Because of course these two still live in the same space-time, they live in the same universe, but locally they see very different things because they have this different clock and this different ruler. And therefore, if we translate that we see that if we have nothing for the blue observer, we get this thermal spectrum for the red observer. And that is exactly this Hawking radiation. So to make something of an analogy, we need well, three things. We need this observer, the blue observer, the lazy observer. We need an analogy to the red observer, and we need some process to translate between them. And well, of course, we need a horizon because else there's nothing going on. So that is the key. Those are the key ingredients. Well, the quantum system we use for this is called a tight binding model. So on slide 20, I here have a lattice for you, which has atoms, the blue balls, at position 0 to n. So there are n atoms in total. And now it's a tight binding approximation where you say that around these atoms you also have electrons flying around. And because, well, they're tightly bound to the atom, so they stay close to it and like to sit very close to one of the atoms. However, such an electron can move from one atom to the next. And we say this happens with probability T, J, and J then depends on where it is. So this one here is then the hopping from the one that is circled to the left, for example. And now what we will do is to make all these analogies for these different spacetime is to tune this T. Well, for people that know a bit of quantum mechanics, this is then now the upper thing is how you write the Hamiltonian in second quantized form. But it's not relevant if you have never seen this before. Okay, so on 21, we will look at our first observer, the lazy blue observer that just sees empty space around him, flat space-time. And it turns out that the system that best describes this in quantum mechanics is a constant hopping term. So the probability, the hopping I call T, the probability of hopping from site 3 to 4 is the same as from 8 to 9 and etc. So every site there's an equal probability of hopping to the left and the right. And well, because nothing really interesting is going on, there's never gravity somewhere locally, there's never mass. It kind of makes sense that this is constant because also the gravitational potential is constant. But of course, we need to check this. So what we do is we compare the electronic wave function. So this is the probability on the y-axis on slide 22 for an electron to sit on a position on the lattice. And well, I have an atom with plus charge, an electron with minus charge, so the two will attract. So electrons will want to sit around the atoms, and that's what you can see in the different drawn graphs. And what you have there on the most left upper graph is that there is zero energy, and I've drawn in light green the general relativity solution, and on the darker blue the solution of our quantum system. And in the upper left diagram, you can see that they exactly overlap. So the electrons have a high probability of sitting around the atoms, which is very nice, which is what we expect. Now, if we increase the energy of the system, this still happens, but with a different period, or they will sit a little bit in between them, and there will be more variety, but this costs energy to make. So the ground state or the lowest energy state is then to be at the electronic positions. And what you also see if you compare the higher energy functions, so higher than zero energy, is that the lattice model and the GR model become very differently, right? So in the lower right, they're completely different, while at zero energy, they're completely the same. And this is because even though the systems are very similar, you both have something that is, that is kind of flat, constant, no gravitational potential changes. One system, our quantum system, is very much finite, so it only has n atoms in there, while on the other side, the universe is infinite. So this gives this very different behavior for larger entities. And the larger you make your quantum systems, the longer there is a match, but still only for energies close to zero energy. Okay, you can think it doesn't work for high energy, we can give up, but that would be a bit boring. So we still think as long as we stay to this close energy, we will see similar behavior, and then in the end we will see what is the effect of these higher energy corrections. Okay, so let's go to the second system on page 23. Now we need some kind of analogy for this observer on the rocket, which is accelerating, and therefore it has some kind of horizon. Okay, it turns out that the type binding model that is similar to this is the one which has linear hopping. So the hopping from 0 to 1 is 0, from 1 to 2 is 1, then 2, then 3, then 4, then 5 will multiply with a constant, but it's linearly increasing from the left to the right. Let me show you why I say this is similar to this red observer. If you look at slide 24 and then the lower left picture, you see again this space-time diagram that I showed you before, where I had these light pulses that move towards the horizon but never reach it. Now, if I have my lattice with atoms in a row with these probabilities that are linear, and then I have an electron that I put on one side of the lattice and I give it some kind of energy and I say, okay, do your thing. We will just record what happens in the computer. Then you can see that in the 3D graph in the middle of the slide, that it starts, which is the purple. It starts all the way to the right where we put it, and then it will move towards the left when the time increases, which is the t-bar direction. And then it goes towards this point at 0, where our so-set horizon is. And it becomes smaller, 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 and it approaches 0, 0, 0. And then at some moment when it becomes very orange, it actually starts doing weird things, wiggly things, and that is again because our system has a finite size. But if you cut it off when it's still a bit orange, then you can map this line from purple to orange again on space-time. And then you can actually see that it's exactly the same path that light would take in such a gravitational system. So that's why I say that this is similar to having a horizon there, because we see this behavior of an electron that is moving from one side of the lattice towards the horizon and gets stuck there till other things happen. And again, this only works if we give it if we give the electron that we shoot in low energy, so close to 0. Okay, again, we can also compare the eigenvalues. The eigenvalues, we call them, but the probability of electrons sitting somewhere at different energies. So if you go to slide 25, you see again the probabilities for electrons to sit somewhere on the lattice, and the GR model in light blue and the lattice model in dark blue. And you see that for 0 energy, the left upper one looks very good on top of the other, and it follows exactly the upper atoms, just not the lower ones, which is again something due to the quantum system having a boundary, and the universe having not a known boundary. But if we increase the energy away from 0, they diverge till they become something very, very different on the lower right one. Okay, so again, we have an agreement for the wave functions and also now for the trajectories, but only around 0 energy. So back to our goal on 26, I showed you this graph and I showed you that we need all these things to actually have this Hawking radiation. So let's see how far we are. If we go to 27, I showed you that we have this constant hopping model. And then if you plot the trajectories of electrons in there and of light in GR, you see that they both move straight and nothing weird happens and they're a good match. And at low energies also the wave functions, these probabilities for these electrons match very well. And on the right, I have this second observer where we have linear hopping. And then we also saw that the movement of light and the electrons are the same and that the wave functions map very well for low energy. Okay, but now we need still some radiation. I promised you a radiating synthetic black hole. And to do this, I need to translate between these different clocks and these different rulers in GR. But I'm very stuck in the lab because if we're here on Earth and if I'm in the lab and using quantum mechanics, I don't have two different clocks. I cannot go near a black hole and have a gravitational field mess up my clocks or go with such high accelerations that I will notice any effects, such that I cannot change my time. I have one time and one time only that I can use. And translating between these different observers is not possible. So I have to be smarter and I have to do something different. And what we, instead of changing our person, our observer, did was say, well, what if we don't change time, we don't change our coordinate system, but we say we immediately, instantaneously create a black hole out of nothing. Okay, it sounds ridiculous, but actually it's very interesting to reduce a problem to the core components. If we have only this very simplified things, can we still get out what we need? So it actually forces you to reduce a problem to its necessary components. And I think that's actually very interesting. So if we do it that way, instead of having to change time, we can change our hopping and therefore change the gravitational, the analog gravitational potential. And for example, what you could do is if you have such a lattice with constant hopping, you turn on a magnetic field instantaneously such that your hopping becomes linear instead of constant. And then to get radiation out, you need to compare the amount of particles that you would see. Okay, so on slide 29, I have the results for you. The black line in that figure is the GR expectation value. So that is the Hawking radiation that you would see for a black hole with a certain mass. And it gives the temperature 1 over pi n with n the number of particles in the quantum system or the mass of the black hole. And all the colored dots, those are the results from the analog system. Well, and as I hope you can see, is that they're almost a perfect match. And if you increase n, it becomes only better and better. And you can, in the end, span the whole space. So what you see then is that this is very well the same. So yeah, you have a spectrum which is analog to thermal radiation near black holes, and that is this thermal radiation that Hawking predicted, which is amazing. But if you go to 30, and maybe if you remembered everything well, you might also be very surprised because actually in this picture I plot energy from on the x-axis from minus something to plus and not only close to zero. But for all values of this energy, the approximation works perfectly. Well, before I showed you that only the mapping was good around zero energy. So I only had this horizon and this wave function that worked well with the GR when I had zero energy almost. But the thermal spectrum that I get out is working for all energies. And it's actually even worse because to get that spectrum, I have to sum over all of the energies of one of the system. So it should be all mixed up and higher order effects and only somehow approximating the thermal spectrum, but it does not. And therefore, we know that there must be something more going on. There must be some deeper reason why we get this thermal behavior out, more than just the wave function matching for some energies. Okay, so this is going to be a bit technical, and I skip a lot of the details. If you're interested after in anything that I leave out, just send me an email, or a message here on Clubhouse. But I hope you're still following me a bit. So slide 31. We found the origin of this thermal distribution in a whole different field, somewhere in one of the corners of condensed matter, at a result by Peschel and colleagues, where they look also at the constant hopping model. So again, the probability of electrons hopping from one side to the next is the same for each lattice side. But now, as you can see, I made 2 copies of my system, and that's important. Okay, and if you now go to 32, what I then do, and what Peschel did, is say the left is a part that I'm not interested about. But of course, it was there, and I have one system, so it does have an effect on what I have on the right. But I will only calculate that effect and then leave out all the other things that I know about left. And that's what we call taking or calculating a reduced density matrix. And it tells you something about the entanglement, the relation between the left and the right. And it's this rho r here. And Peschel wrote that as e to the power of hr, with this hr, what we then call the entanglement Hamiltonian, but it's just a name. And that measures the amount of entanglement between the left part of the system and the right part of the system. And now what Peschel showed very nicely is that this hr is thermal for the constant hopping model. So it gives you exactly this thermal spectrum, the black line that we saw before in our results. Okay, so there are already 2 parts. Maybe you can think about it of the inside and outside of the black hole, but how does it connect to our system? Well, if you go to 33, this HR turned out to be exactly our linear hopping model. So there's a very special relation between the entanglement of the initial system with the constant hopping towards the final system when we turn on this magnetic field and therefore create a horizon. And that is that the second system is the entanglement Hamiltonian of the original system. And therefore, because of this relation, you get a thermal spectrum. Okay, so maybe we've learned something, but we need to put this to the test, right? So on 34, I plotted, or I show you a different system, which still is a tight binding model, but instead of having linear hopping between 2 sides for the electrons, we have quadratic hopping. And again, you can plot these trajectories, and again, you can see, there's a horizon. So if there is a horizon, I suspect radiation, right? Because that's what I told you. If I have these 2 observers and one of them has a horizon, then they will see radiation. Okay, let's put this to the test. On 35, I have the result for you on the quantum system. And I show you on the green dots the results from the quantum system, and on the black what we would expect from GR. And you can see that they look, well, qualitatively definitely not the same. One curves a lot more than the other, and therefore something weird happens. The green solid line is the difference between the 2. And thus, indeed, our prediction was right. If we take a different form of the hopping, such that the relation between the 2 systems is not the one described by Peschel, we do not get this nice thermal spectrum. And that was something new, because we did not expect this. We actually expected that if we have a synthetic horizon and we have this horizon behavior, it would always work. But it does not. So let's see if we can actually learn something about this. Okay, in 36, I summarize a bit what we have. So you have this lattice, and then you have constant hopping, and that was something equal to flat spacetime. Then if you have linear hopping, we have this very nice thermal spectrum. And if we have something other, such as this quadratic hopping, then we do not have a thermal spectrum anymore, even though we do have a horizon. And it turns out that this linear hopping has this horizon behavior, which is exactly the same as a very special kind of space-time in GR. If you go to 37, you can see it, which is the space-time and the time and distance that an observer would see standing on this rocket. And this rocket then has acceleration a, which is constant. If this a is not constant but changing, then you might get these quadratic terms. But as long as it's constant, it's always till first order a linear hopping model, and therefore for all constant accelerations, you get you get this thermal spectrum, or that's what we predict with the quantum theory. Okay, so that is already nice, and it's already something interesting to consider, because in GR we don't have access to changing acceleration, because it's very hard to do that with the theory of GR. So we normally only or almost only consider things with constant acceleration, and now in this different system we have a lot more access to that. We can actually do some of the calculations or do the numerics. So that is already a nice result. But second of all, we also found out that at least in the quantum analog, it's very important to have this entanglement structure. So we started out by calculating something with entanglement of the two initial systems, and then found out that there's a very special relation that gives you this thermal behavior. And therefore, this might also be an opportunity to learn more about entanglement in black holes and how that behaves. Maybe there is a special entanglement structure that also dictates how Hawking radiation looks, and this could be a place to search from it. Yeah, and also we can go into requirements for Hawking radiation. So what is necessary to actually get this radiation out? Because only horizon was definitely not enough. So that brings me to the first conclusion and kind of like the end of the paper we published. We'll go a bit on to future research after this, but this is like the in-between conclusion, which is that we have this synthetic horizon, and then indeed you can get a thermal spectrum out. But this is a very special case where we have this result by Peschel, called the thermalization theorem, and only when you have this special relation between the two systems and between the entanglement, then you get the thermal spectrum out. And therefore, not all of the synthetic horizon, not all horizons you can think of will give you it. Okay, well, I promise you experiments. So in 39, I give you a sneak preview, because this is all research that is going on, and that is definitely not published or done yet. But we're now working together with the experimental group in Dresden, where we're trying to actually make these systems and see if we can get this radiation out. Okay, the setup you see on 39 is not the complete setup that we will use, but it has the same components. So I thought you would maybe be interesting to see that a bit, how something like that would look. And we'll just use electronic components, such as, just think about that you have currents and resistors and capacitors, and you change that in such a way that you can mimic what I've told you so far. Okay, well, what do we want from this? Well, this experiment is completely classical, and Hawking radiation is partly a quantum effect. So it's a big question if we can actually still see this radiation if we do not consider anything quantum, and that is interesting to answer. So that is one of the questions that we hope to answer with this kind of experiments, and it would also be amazing to see this radiation in experiment itself. Okay, and also we learned something about the entanglement being very important. So that is something that is definitely worth doing more research on. Okay, but one of the holy grails of analog black hole research is looking into evaporation. So because black holes radiate out radiation, and we also have something called energy conservation that all of you are familiar with, we think that black holes must evaporate. They must lose mass, and therefore in the end disappear. And this brings all kinds of problems with it, which are summarized by the black hole information paradox. And therefore, people have been working on this for years, and it's very hard. And therefore, people are very interested to see how this would look like in black hole analogs. Can we manipulate this in the lab in the end as well? But it's also really hard, because if you go to 41, you need a lot of things for this evaporation. Okay, so a bit technical terms, but the first requirement is basically that we have space-time. And so far, what I've all shown you is more manipulating of gravitational potential in space. And I don't really have anything with time. Like I said, I only have one clock here. So you need to be very creative to change this. The second thing is that you need a horizon. Well, we have that. Slow evolution of a black hole creation. You can do that by tuning the magnetic field very slowly, for example. The fourth one is basically that there is actually something massive that can evaporate. So in the system we consider, we only have a horizon, just like the waterfall basically had only a horizon and everything fall away. And you need something massive if you want to lose energy, because else nothing can evaporate. More things are still necessary to see this in a lab. But actually, soon on arXiv we will publish a paper where we also show that we need even more for this, which is very interesting, and which is an answer we hope also to answer with this kind of research on analog black hole. So slide 43. So we started actually with the first thing, which is to include time, and we hired a new PhD project, PhD student Lizzie, who is now trying to find a quantization of space-time. So what I showed you, I have atoms on a lattice, so they're all a fixed distance away from each other, and therefore I say they're quantized. There's one, and then there's nothing, and there's another one. While space normally is kind of continuous, or we think about it that way in GR. But time is still time. Time I still have in the clocks around me, and therefore to go to this special GR treatment, we also need to quantize time, and this is hard, and therefore we're starting off this new project to try to find a system that can do that, which I think is a very exciting new way of going. Okay, let me summarize what I've told you. So we found a synthetic black hole model that has a horizon, and it has an analog to Hawking radiation. And we learned from this that you can create synthetic horizons in multiple ways, but not all of them will give this Hawking radiation. And this gives us a very good starting place to start more research on Hawking radiation, and even in the end, black hole evaporation. And also to study our theories and all the requirements in the lab. And I would be happy to answer any questions you still have, but I hope you followed at least a bit of it. Thank you.
Thank you so much, Lotte, for this wonderful presentation where you explained the principles of black holes all the way to your, cutting edge research, which was really wonderful and makes things way better to understand, I think, at least from my point of view. And I'm checking really quick first in the chat what people are asking. Let's start with Oppenheimer's question, and then I'll go to the questions I have written down also from people. Oppenheimer asks, are you able to solve this problem where singularity is having infinite density with no mass? He's I don't know if it's too far away from what we're discussing. Just let us know, and we'll continue.
So if I understand your question completely, is that in a black hole you have an infinite density? Well, there is mass there, and we do not have infinite density because we also do not have mass. And instead of having a real density and real gravity there, there is another way how things move. So therefore there's no real mass there. So maybe the answer is your question. I'm talking about center of black hole. So the real black hole or the analog one?
Yeah, I guess Oppenheimer is talking about the real black hole and the center of
Okay.
a black hole. Yeah.
So in a real black hole, there is a mass. Yeah. And well, we don't know exactly what is going on at the singularity. Also, it's behind the horizon, so it's very hard to know anything about it. Yeah, and that's behind the scope of this kind of theory, because we're really interested in what can we see outside of the horizon and not really what happens at the singularity itself. But of course, that's a really good research field as well.
Yeah, thank you so much, Oppenheimer. I hope that answered the question in that regard. So, I think that it's really interesting how you describe, um, this hopping. And is it correct? I don't know if it is, but is that a similar mechanism how we know how hopping is important for, let's say, ATP production in the cell, or is that completely out of very, very different, type of mechanism?
Well, so you probably can describe the ATP production with a similar model as I showed you. However, where this hopping comes from and what actually hops, that is then completely different. So here the hopping is due to quantum tunneling and quantum effects. And there, well, it would be mostly classical effects inside the body and chemistry that I don't have a grasp of. But there, like in the field of biophysics, there are a lot of people that try to describe systems, mostly in the brain, but also in other types of chemistry processes with quantum mechanics, and then to see, can we use methods of one or the other to answer something for both?
Yeah, I think that's really interesting. Just as a side note, that is really interesting um, in general. And if you can think of the next steps you want to go in, and maybe technological developments you would like to have for your continued research, what would you wish for, and what would you know have next, like if there would be infinitive grants and money and so on?
And time. um, so we're also talking with a group in Amsterdam about trying to start up a project where we, instead of doing some classical experiments, we work with cold atoms. And well, they're experts on that in the lab in Amsterdam. So they're thinking if they can actually do something like this. And I would really like to continue that, because I think there we will can see the full scope of these quantum effects, and also compare it then with the classical experiment will be very nice. But it's not off the ground yet, so I don't know the details or if it's going anywhere in the end.
Yeah, that's interesting. And um, for this radiation of black holes, do you expect that for all kinds of sizes of black holes there would be a similar mechanism? Because why I'm asking this is, we had the speaker here before. He talked about that there could possibly be peaks of dark matter around black holes, and he kind of showed the mathematical model how, you know, this could be possibly true by the drag of how different planets, like if two planets get dragged in, how the forces of basically the gravity of the black holes have different effects on if two planets together would get dragged in. One would, the other one could escape, and he models that this could be due to peaks in dark matter. So would you expect that to have an effect, and would there be a way for your model, like your analog black hole, to kind of look into that too?
Well, so the connection with dark matter is always a bit hard, right? Because we don't know what matter is. There are a lot of very good theories, but we haven't found it, and therefore none of them is confirmed yet. So to know how dark matter influences the behavior of black holes, you need to assume what it is, and mostly what is the mass and how does it interact with other fields. Um, so yeah, you would have to choose a model and then go from there. And that's probably what your last speaker very beautifully did. But therefore, I can't say what would happen because I don't know what is the nature there, and I don't know all the models by heart.
Yeah, thank you for that, and for that answer. And Ash is asking, I don't know, you please get back to me if the questions, you know, are too far out of, you know, your research area.
I will just tell you when I don't know something, and then
Yeah.
you can ask me anything.
How would you quantize space-time, and if you could expand on Lorentz boosts?
Yes, good question. So that is the start of the new PhD project that I just mentioned, indeed. It's hard. Let me start with that. But what we are kind of trying to do is to find a lattice that respects exactly these Lorentz boosts, so the symmetries of spacetime, such that you have to kind of find a way of slicing your lattice, so turning your axis that preserves these boosts and these symmetries. And well, one way of looking at this with constant gravity is with kaleidoscopes. If you're very interested, you can look that up, which is a process where you put all these kind of mirrors, and then you kind of make a spacing that is quantized and then preserve some of the symmetries. And this is one of the methods that we're now looking into, but we have to expand that then to non-constant gravity, because else we do not have black holes. But yeah, starting with respecting the symmetries of the universe inside a lattice, that is kind of the starting point that we want to go from. And those are these Lorentz boosts.
Yeah, thank you so much for that question. And then Oppenheimer asked if you could talk a little bit more about the other side of the black hole. But again, if it's, you know, I know you're interested in the radiation, so just let us.
You mean, I think that you mean the inside. Yeah, indeed, it's not in the model. Um, and I don't have a theory for it, because you need quantum gravity to actually do a theory in real black holes, and we also haven't figured that out. But yeah.
Yeah, thank you. Yeah, if anyone has more questions, please raise your hand, and we will take your questions. And yeah, if you like you mentioned that this entanglement, or is it Hamiltonian entanglement? is really, important for this system. Could you, I don't know, I'm probably, it's really not my field. So could you explain how did this entanglement happen and why, or is that known? And again, why that is such an important factor, because I think that's really interesting to me, at least. I read, you know, a couple of years ago, I read like, different public, general public books about entanglement and, quantum physics. So I thought that was kind of a really interesting part of your presentation.
Yes, I think it's also an interesting field. So the entanglement is there before you turn on the magnetic field. So if you have a big system, everything can move from the left to the right and nothing weird is going on. But if I have two balls inside a classical system, for example, then and they bump into each other, then one will go to the right and one will go to the left. So they have an effect on each other because they can interact everywhere. And of course that's classical, but in quantum, well, entanglement is the analog of this, such that everything on the left and the right affects each other. And then what I do, if you create a horizon, or if you then you certainly cannot see anything on the left side of the system anymore, because because you cannot pass it. There is a horizon, and then there's a region where I cannot go. But before I had this horizon, these two regions were related to each other, and now certainly they're not. Or well, yeah, they cannot interact anymore, and it's this breaking of these two regions that is introducing the entanglement in the problem, and therefore it's important, and also that is the reason why we get the thermal behavior out. And it's more that we found out that in the quantum system, the entanglement is the only way to get this thermal radiation. In the GR system, in real black holes, we cannot be so sure. That is for other experts to say. But therefore, I think it's fundamental to look into these questions.
That's really interesting. And then, yeah, I have two questions, like two follow-up questions. So, can you then learn, like, since there's an entanglement, can you learn then from the part that you can still detect and observe about, the part that you cannot anymore? So the inner works of the black hole, the other side, can you learn from them since they are probably still entangled, or is the break really that the entanglement breaks and you cannot learn anymore from the other half, or the ones that are still entangled, but you can still observe?
The entanglement was due to them being connected in the past. So you can learn something about what was happening in the past to the other side of the system. So before it got broken. So if the balls in the classical example did collide or not, you will probably see. And then you also know, oh, I had a ball on the right, so now I know that I also have a ball on the left. But then inside the region that you cannot see anymore, all kinds of things might be happening because, well, it's black hole physics, so there will be all kinds of quantum gravity and weird stuff going around. So then I don't know what happened to the left ball, but I knew that the left ball and the right ball collided in the past. So you can learn something about what it was before it got broken, but not after.
Okay, that's interesting. And so since you needed the entanglement before, is there is the universe just holding together and working because at some point everything was entangled at some point? So did you need that connection in the past to begin with for anything to exist? And be in the universe? I think that's a very interesting philosophical question.
Well, it needs to be there for Hawking radiation, right? So the existence of the universe, I wouldn't tie to it. But yeah, I mean, entanglement is everywhere, and we don't know the extent to it close to the Big Bang. But it's definitely interesting to see. And one of the things that you see is that the early entanglement between parts is visible in a TMB for the cosmic microwave background, which is something we can still observe today. It's kind of the baby picture of the universe, they say. And entanglement there is also a big subject of the research. So I think it's important in our world, and that it has a huge effect because it's well, the weirdest quantum effect we have. Um, yeah. So, but if it's necessary for a universe to exist, I don't dare to say that.
Yeah, thank you. I knew that you would. I mean, that would be, but it's interesting to think about. At least for me, it's interesting. And then how do the results of your experiments and your theory, um, the interplay between quantum mechanical and the gravitational aspects, how do they, pave the way or give us insights, or are there implications for the broader field of, quantum physics and gravitational theory that you expect to come out of this research?
Yeah, so if we are able to do the experiment classically, and we don't see any radiation, then we know that somewhere we made a very important assumption of something being quantum mechanical, and that is one of the requirements for having Hawking radiation. Well, if we know that we can actually do it classically, then we can make a classical approximation of this Hawking radiation. So that will tell us something about the nature of this radiation and possibly then also evaporation. So that is something that in the future we can learn. And also, of course, that we need to research more about the entanglement structures of 4 min black holes, because that's kind of what we did here, looking at the entanglement structure before and then saying, therefore it becomes thermal after. So maybe that's a different way of deriving Hawking radiation.
Yeah, it's really interesting. Thank you so much for your presentation and also for answering the question. And I'm just checking really quick the chat one more time. Um, oh, yeah, Oppenheimer just added information about entanglement. So, yeah, if anyone has follow-up questions also in the future for future listeners, just reach out to me if we didn't cover something, and then we might be able to cover it in the future or answer in the future. And lots of thank you so much for this really amazing presentation and for sharing, this really cool work of yours that really, um, yeah, enlightens us a little bit more. So it's, how the universe works. Um, and yeah, I wish you all the best for your future. And I hope we'll stay in touch and we'll follow your work to see what the next experiments will hold for us in the future. Thank you.
Yes, thank you all also for listening and for the invitation. It was great to be here. And if you have any questions to me, you can always find me on my website, lottemertens.com, or there's also my email on there. Yeah, and I would be happy to answer anything you still want to know. And indeed, I also hope we keep in touch and I can present some very nice results if I have them. So thank you all.
Yeah, thank you. Yeah, whatever your results are will be, something new we didn't know before. So it will be always great. And yeah, and thank you everyone for coming and asking questions and posting comments. And I hope I hear you all again soon. So thanks everyone. Lotte, it was such a pleasure having you, and I'll close the room in 3, 2, 1. Bye, everyone. Thank you.